Hi everyone, my name is Fatima. I'm presenting our paper which is about nucleus decomposition in probabilistic graphs. Probabilistic graphs are graphs in which each edge has a probability of existence independent of other edges in the graph. These graphs arise in many applications such as biological, social, and trust networks. For probabilistic graphs, we have the concept of possible words, which are just deterministic instances of the original graph in which a subset of edges can appear. K-core, K-truss, and K-nucleus are popular notions of dense subgraph in the literature. K-core is a subgraph in which each vertex has degree at least k, and K-truss is a subgraph in which each edge has at least k triangles. Here, for this graph, you can see different core and truss decompositions. And also we have notions of K-RNS nucleus, which is a generalization of core and truss notions, and in which each arc-helix is contained in at least k number of S-helix, and each two arc-helix are connected through a sequence of S-helix. The most interesting subgraphs in terms of density and hierarchical structure is K3 and 4 nucleus, which is denser than core and truss. Here in this figure, you can see 1, 3, and 4 nucleus subgraphs, which are actually reported as separate subgraphs because triangles in these two subgraphs don't share a fork-helix. Also, if you apply core and truss decomposition, the whole graph would be corresponds to 3 core and 2 truss. So in this paper, we consider only K3 and 4 nucleus for probabilistic graphs, and we simply call it K nucleus. So we propose 3 different notions for probabilistic nucleus. The first one is local K and theta nucleus, in which each triangle is contained in at least k number of fork-helix over all the possible words with high probability. Consider these probabilistic graphs with different edge probabilities and threshold 0.13. The whole graph corresponds to a local nucleus where k is equal to 2 and threshold is 0.13. Each triangle is contained in 2 of fork-helix with probability no less than theta. For instance, if you consider triangle 3, 5, 6, it is contained in fork-helix by vertices 3, 5, 6, 4, and another one by vertices 3, 5, 6, 8. If it is contained in these 2 fork-helix, if all the edges in these 2 helix exist. So this requires multiplying 9 of these blue edges, which gives us a probability greater than the threshold. This version is local because we consider triangles independently and we don't have any constraint on the possible words global wise. So we tackle this problem using another definition which we call global nucleus, in which we are looking for finding a subgraph in which each triangle has enough probability to be contained in the possible words of edge which are deterministic K3 and 4 nucleus. This definition is a strict definition, and we also tackle or actually relax this global requirements by requiring that the possible words only contain a deterministic K3 and 4 nucleus. Using these two global-wise definition, we ensure more cohesiveness. Here, subgraph H a smaller part of the graph in the previous slide corresponds to a weakly global, and this graph can be verified that cannot be a global nucleus because some of the triangles, like triangle by vertices 1, 2, 3, cannot be part of and cannot have enough support to be part of many possible worlds which are deterministic K3 and 4 nucleus. But a smaller subgraphs, H1 and H2, which are induced by vertices 1, 2, 3, 4, 7, and 2, 3, 4, 6, and 7 are considered as global nuclei. In fact, the only possible worlds which is deterministic 2, 3, and 4 nucleus is the one in which all the edges exist, and the probability of existence of this graph is greater than our threshold. As can be seen, weakly global and global nucleus decomposition can find smaller subgraphs missed by local nucleus decomposition. For local nucleus decomposition, we have definition called probabilistic support for a triangle, which is the maximum value of K such that the triangle is contained in at least K 4 cliques with probability no less than eta. And then we have set of all 4 cliques contain delta, contain triangle, which we show with S or S of delta. And we have a nucleus score, which is the maximum value of K such that the triangle is contained in the corresponding K and theta nucleus, in the local K and theta nucleus. The main challenge is computing these probability values. We use dynamic programming or simply as DP approach to solve this problem based on the observation that a triangle is contained in K of 4 cliques from arbitrary subset S1 and Sj. And this event can be expressed as the union of 2 sub-events. The first one is that Sj in this set can exist and the triangle is contained in K minus 1 of 4 cliques from this set, or Sj does not exist and triangle is contained in K of 4 cliques from S1 up to Sj minus 1. And then using these 2 events and considering the probability of existence of these 2 events, we obtain a recursive formula for computing this probability for different values of K. The DP approach is quadratic in the size of all in the size of cliques which contain a triangle, in the size of actually 4 cliques which contains a triangle. So we obtain more improvement using some statistical approximation. By utilizing that support of a triangle is a random variable which can assign different K values with different probabilities. So here in this figure, consider triangle with vertices U, V, W, and this is a clique which contains that triangle. Corresponding this clique, we define a Bernoulli random variable which can takes on 1 if edges from U to Zi, V to Zi, and W to Zi exist. And then using this formula, we relate, we make a relation between the sum of these Bernoulli random variables and support of each triangle. And then using statistical approximations, we approximate the distribution of this sum using well-known statistical distributions such as Poisson, normal, and binomial distributions. In order to find the local nucleus decomposition, we use peeling approach, which is a general strategy used in probabilistic quartz, Ross, and deterministic nucleus decomposition. So the main idea is that triangles are processed based on their probabilistic support, and we recursively process triangle with the smallest probabilistic support. Once a triangle is processed, its nucleus score is said to be its probabilistic support at the time of processing. And then we find triangles which form a fork helix with that triangle being processed. And then we update probabilistic support of those triangles. And once a nucleus score of all the triangles is obtained, we can simply build local K and theta nuclei for all values of K. Regarding global and weakly global nucleus decomposition, the general idea is that we observe that local nucleus subgraph can be a good candidate for global and weakly global. This is because we prove that each global or weakly global subgraph is a local nucleus as well. So once we extract local nuclei candidates, we use Monte Carlo sampling to obtain samples of these candidates. And then for each candidate, candidate H, we check that whether triangles in H are contained in enough number of samples that are deterministic K3 and 4 nucleus or contains a deterministic K3 and 4 nucleus. Here in this slide, I show our dataset statistics. Kurgan, Flickr, DBLP, Biomine contain probability values, but for the rest of the dataset, we generate probability values randomly. Here in this slide, we show cohesiveness of our nucleus notions in terms of probabilistic clustering coefficient, PCC, and probabilistic density. As you can see, the global nucleus, which is shown in the red bar chart, has the highest density and PCC. And after that, weakly global obtained is much cohesive, is more cohesive compared to local version. We also apply nucleus decomposition on human Biomine dataset. This dataset is a dataset which contains human proteins or genes and interaction among them. We consider proteins that has literature support for their interaction with coronavirus. These proteins are given here, which are from a UniProt database. We find the subgraphs obtained by local, weakly global, and global nucleus decomposition, which contains these three nodes. Here is the subgraph. The whole graph is a weakly global nucleus, and the pink nodes and edges among them corresponds to a global nucleus. And then this result is very interesting. We try to find some gene analysis to find the diseases that can be associated with these proteins. And we realize that these proteins in these subgraphs can be associated with some specific cancer. And this observation is good, can be used by biologists to see whether the treatment for, whether the drugs for treatment of these disease can be repurposed for treatment of COVID-19 or not. Here in this slide, we also compare our nucleus decomposition with their counterparts, probabilistic truss and core. So we have local core and local truss, as well as global core and global truss. And here we report maximum K, which is the maximum value of K such that the corresponding subgraph contains portents of interest, and this is the number of nodes and probabilistic density. As can be seen, local nucleus is is denser and also smaller than local core truss as well as global core. Also, our weakly global and global nucleus subgraphs are smaller and denser than global truss as well. And another case study that we considered is the problem of task-driven team formation problem. We consider DBLP collaboration network. Vertices are authors and edges represent the collaboration level in the papers co-authored by a pair of authors related to a given task. We have query Q and T, where T is a set of keywords describing a task and Q is a set of vertices. And the goal for this problem is to find a set of vertices that contains Q and make a good team to perform the task which is described by the set of keywords in T. So we solve this problem using our purpose nucleus decomposition definitions. Here you can see two queries. For both of them, we use keyword algorithm, and query vertices are different. On the left, you can see that the whole graph, thick blue and black edges, corresponds to a local nucleus subgraph, which is the same as a weakly global subgraph here. And also the graph in blue corresponds to a global nucleus subgraph. Also on the right, you can see our weakly global nucleus subgraph, which contains these authors as well as the other authors. For both of these graphs, you can see that all these academians have good affinity to collaborate on a paper research related to algorithm. And also we observed that people in this smaller blue subgraph, collaboration between them is more focused on data structures. Here on the right, we realize that for this query, local nucleus decomposition gives graphs which are bigger and has 100 nodes, and also global nucleus, we couldn't find any subgraph using global nucleus subgraph nucleus decomposition. So in this example, we want to show that weakly global can find a very good teams when local or global definitions provide teams that are very big or too small or even empty. So in conclusion, we introduced three notions, namely local, weakly global, and global. We show that the computing weakly global and global are interactable, and we propose efficient algorithm based on Monte Carlo sampling. We design a polynomial time algorithm, peeling approach, which is based on dynamic programming. We also improved its efficiency using statistical approximation. We evaluated the efficiency, scalability, and accuracy of our algorithm for nucleus decomposition on real-world dataset. Thank you for your attention.